Hi, my name is Jacob Schaefer, Chief of Software at Gears Inc. We programmed a robot in Simulink to make use of its graphic interface in simulation mode. Our program this year is designed to give our robot, the R10A Radian, the ability to drive throughout the field, raise and lower an arm, open and close independent sides of its claw, and autonomously deliver spare insulators. We divided our program into 4 subsystems, each representing a division of the robot's control system. All of them are linked to this one, the extra controls subsystem. It houses the extra controls we added to our program to improve user interface. The first is left-handed control mode, in which several buttons switch sides of the gamepad. To prevent accidental activation, it is not entered unless a sequence with 3 buttons is completed. Another extra feature is precision mode, which divides output to the motors in half for more detailed control over the robot's movement. This switch disables precision mode during autonomous mode. Switches like this were put in several other places in our program for the same purpose. The third and final feature is simulation mode control. During a simulation, operators can use the Logitech gamepad to simulate the input of the VEX controller. We also included virtual controls for cases where the Logitech gamepad is unavailable. Now let's look at the drive subsystem. Our robot utilizes a 2-wheel tank drive system in which each motor is controlled separately from the other. We use the gamepad joystick to control each drive motor. These deadband blocks neutralize low inputs from the gamepad to help extend battery life and decrease motor noise. This digital input block reads the input from the 2 bumper switches on the front of our robot. These represent the infrared sensors that were added for an unused line following function. All of these blocks connect to the state flow chart. This chart contains 2 states. The first allows the values from the joysticks to pass through unchanged. The second state is entered when the trigger button is pressed and tells the rest of the program that autonomous mode is active, disabling all control by the driver. This state first drives the robot to the foot of a tower. Our robot was tested and proven capable of following the black and white lines on the field. Due to a strategy change, it was decided that a dead reckoning would be more efficient, but the capability was left in a program in the event that it was needed again. After one of the bumper switches contacts the tower, it tells the robot to drop the spare insulator back away from the tower and stop its wheels. Control is then automatically returned to the driver, although autonomous mode can also be manually interrupted by moving the joysticks. After passing through the state flow chart, the values from the joysticks go to these switches, which cut the values in half when precision mode is activated. The values are then sent to the motors, one of them being inverted for the right motor since it is on the opposite side of a robot. Now let's take a look at the arm subsystem. These gamepad buttons are used to raise and lower the arm at full speed. The signal from these buttons first goes to the switch, which disables this function when they are used to activate left-handed control mode. The value is then reduced during precision mode. This value is then sent to the arm motors, being inverted for one motor since it is on the opposite side of a robot. This section of the program was implemented to test an idea for a wrist. Although it was not used in our final design, it was left in the program for later improvements. Now let's look at the claw subsystem. The signal from these gamepad buttons is sent to this state flow chart. It toggles between 2 positions for each side of a robot's claw during driver control, but during autonomous mode, it gives the claw servos values from the driver autonomous control chart and the drive subsystem. This concludes the presentation of our Simulink model. Thank you for watching!